December 5, 2016. Mountain View, California. A crowd of aerospace engineers, NASA officials, and venture capitalists gathered in a nondescript conference room to witness something that conventional wisdom said was impossible. On a projection screen, complex diagrams showed a propulsion system that could theoretically accelerate a spacecraft to 1/10 the speed of light. The presenter wasn't a seasoned aerospace veteran from Lockheed Martin or Boeing. He was a 32-year-old nuclear scientist named Ryan Weed, and he had just promised to build an engine powered by antimatter, the most energy-dense material in the universe. The reactions ranged from skeptical silence to outright dismissal. Antimatter propulsion had been the realm of science fiction for decades. Star Trek's Enterprise, angels and demons, pure fantasy. The mathematics were theoretically sound, but the practical challenges seemed insurmountable. Yet here stood Weed, co-founder of a startup called Positron Dynamics, claiming he had found a way around the fundamental problems that had stalled antimatter research for half a century. Among those watching was Dr. Robert Frisby, a 40-year veteran of NASA's Jet Propulsion Laboratory, who had literally written the textbook on advanced propulsion concepts. He had studied antimatter engines since the 1980s. He knew every reason why they couldn't work. The antimatter storage problem alone had defeated generations of physicists. As Weed concluded his presentation, Frisby remained in his seat, arms crossed, his expression revealing nothing. But his mind was racing through the implications of what he'd just heard. The journey from impossibility to breakthrough began not in a laboratory, but in a moment of frustration. It was 2013, and Ryan Weed was a doctoral student at the University of Michigan working on fusion propulsion concepts. Every calculation he ran into the same wall, the rocket equation. This mathematical law, formulated by Russian scientist Konstantin Tsiolkovsky in 1897, governs all conventional propulsion. It states that for every kilogram you want to accelerate to high speeds, you need exponentially more propellant. The numbers for interstellar travel were brutal. To reach just 10% of light speed, the minimum needed to make Alpha Centauri reachable within a human lifetime. Conventional rockets would require millions of tons of propellant for every ton of payload. Even advanced fusion concepts barely improved the situation. Weed spent nights staring at his calculations, running simulations on university computers, searching for some loophole in the physics. There wasn't one. The rocket equation was as fundamental as gravity. Then, during a late-night research session, Weed encountered a declassified NASA study from 1999. The paper, authored by physicist Gerald Gaidos and a team from Pennsylvania State University, outlined something called antimatter catalyzed fusion. The concept was elegant in its simplicity. Use tiny amounts of antimatter not as the primary fuel, but as a trigger to initiate fusion reactions. The antimatter would provide the immense energy needed to overcome the electrostatic repulsion between hydrogen nuclei, allowing them to fuse at temperatures and pressures far lower than conventional fusion required. The energy density numbers were staggering. When matter and antimatter meet, they annihilate each other in a burst of pure energy according to Einstein's equation E = mc2. 1 gram of antimatter reacting with 1 gram of matter releases the same energy as a 43 kiloton nuclear bomb. For comparison, the chemical energy in rocket fuel releases about 10 megajoules per kilogram. Nuclear fission releases about 80 terajoules per kilogram. Antimatter annihilation releases 90,000 terajoules per kilogram, nearly 1,000,000 times more energetic than nuclear fission. Weed realized that if he could solve just 3 problems, antimatter propulsion might actually be possible. producing antimatter efficiently, storing it safely, and controlling the annihilation reaction. The conventional approach, building massive particle accelerators like CERN's facilities, was economically impossible. CERN had spent hundreds of millions of Swiss francs to produce approximately 1/1000th of a gram of antimatter. At that rate, producing the kilogram of antimatter needed for an interstellar mission would cost more than the entire global economy. But Weed had noticed something in the physics literature that others had overlooked. Certain radioactive isotopes naturally emit positrons, the antimatter equivalent of electrons as they decay. Isotopes like potassium-40, copper-64, and particularly krypton-79 continuously generate positrons without requiring billion-dollar particle accelerators. The positrons were already there, being created by natural radioactive decay. The question was whether they could be captured and accumulated in useful quantities. Traditional antimatter traps used at CERN employed powerful magnetic fields to contain antiprotons or antihydrogen atoms. These penning traps required superconducting magnets cooled to near absolute zero and could hold only microscopic quantities for brief periods. Any contact between antimatter and the trap walls resulted in instant annihilation. The technology worked for physics experiments, but was completely impractical for spacecraft propulsion. Weed's key insight came from his background in nuclear engineering rather than particle physics. He had spent years studying how different materials interact with various types of radiation. He knew that certain crystalline structures could slow down and temporarily trap charged particles. What if antimatter could be embedded in a solid matrix, a material specifically designed to separate antimatter particles and prevent them from encountering normal matter until deliberately released? The concept defied conventional wisdom in antimatter research, which assumed antimatter had to be suspended in vacuum using magnetic fields. But Weed's calculations suggested that carefully engineered materials with specific crystal structures and electromagnetic properties might create microscopic chambers where individual positrons could exist, separated from matter by quantum mechanical effects. In early 2014, Weed left his doctoral program to pursue the idea full-time. He convinced Dr. Josh Machacek, a physicist specializing in plasma dynamics, to join him as co-founder. They named their startup Positron Dynamics and began working out of a shared laboratory space in Livermore, California. Their immediate goal wasn't to build a Starship engine. It was to answer a single question: could positrons be captured from radioisotope decay and stored long enough to be useful? The first experiments were conducted on equipment that looked more like a high school science project than cutting-edge aerospace research. Machacek had constructed a vacuum chamber from salvaged parts. Inside, a small sample of a copper-64 isotope sat in a holder surrounded by experimental trapping materials Weed had synthesized. Electromagnetic sensors monitored the chamber, searching for the distinctive signature of positron annihilation 2 gamma rays shooting out in opposite directions at exactly 501 kilo-electron volts. For months, the experiments produced nothing but frustration. The positrons were being emitted from the radioactive source. That much was certain from independent measurements. But they were annihilating almost immediately upon contact with the trapping materials. Each failure meant redesigning the material's structure, ordering new samples, waiting weeks for fabrication, then testing again. By summer 2014, Positron Dynamics had burned through its initial funding with no successful demonstration. Weed took a position as a nuclear scientist at Draper Laboratory in Cambridge, Massachusetts, to fund continued research. He and Machacek worked nights and weekends, refining their approach. The breakthrough came in October 2014, almost by accident. Machacek had been testing a new carbon-based matrix material with a specific crystallographic structure. The theory was that the carbon lattice might create regions of electron depletion where positrons could exist temporarily without immediately encountering electrons and annihilating. During one test run, the gamma-ray detectors showed an unusual pattern: the expected burst of annihilation events, but then a gradual tapering rather than an immediate cutoff. Something was delaying the annihilation process. Over the next 3 months, Weed and Machacek refined the material, adjusting its composition and structure. By January 2015, they had achieved positron lifetimes of several milliseconds an eternity in antimatter physics. More importantly, the number of positrons being captured was increasing with each iteration. They were approaching a regime where the accumulation rate might exceed the annihilation rate, allowing a net buildup of stored antimatter. The physics community's reaction was measured skepticism. At a conference in April 2015, Weed presented preliminary results to a room of plasma physicists and propulsion researchers. The questions came rapid fire. What was the storage efficiency? How did they prevent cascade annihilations? Could the approach scale up? What about radiation shielding? Weed answered methodically, acknowledging uncertainties while emphasizing the fundamental viability of the approach. Dr. Harold White, director of NASA's Advanced Propulsion Physics Laboratory at Johnson Space Center, attended that presentation. White had spent years investigating exotic propulsion concepts, including warp drives and vacuum energy. He recognized that Weed's approach, unlike many advanced propulsion schemes, didn't require new physics. It required engineering solutions to very hard but potentially solvable problems. In June 2015, NASA awarded Positron Dynamics a Phase 1 grant through the Innovative Advanced Concepts Program. The $100,000 award funded 9 months of research to demonstrate proof of concept. The grant application had outlined an ambitious goal: prove that positrons could be generated from radioisotope sources, captured in engineered materials, and released on demand to catalyze fusion reactions. The NASA funding transformed positron dynamics from a garage startup into a serious research effort. Weed and Machacek hired 3 graduate students and leased proper laboratory space in Mountain View. They acquired professional-grade vacuum equipment, gamma spectroscopy systems, and materials fabrication capabilities. By fall 2015, they were running systematic experiments, methodically documenting results, building the evidence NASA would need to justify continued funding. The storage problem began yielding to sustained engineering effort. By early 2016, they had achieved positron storage times exceeding 1 second long enough for practical applications. The storage materials, now in their 15th major iteration, consisted of engineered nanomaterials with carefully designed electromagnetic properties. Positrons were captured in microscopic voids within the crystal structure, held away from matter by electric fields generated by the material itself. The next challenge was controlled release. For propulsion applications, the positrons needed to be extractable on demand and directed into a reaction chamber where they would catalyze fusion. This required designing electromagnetic systems that could selectively destabilize the trapping sites, allowing positrons to escape in a controlled stream rather than annihilating within the storage material itself. By June 2016, positron dynamics had demonstrated the complete chain: radioisotope positron generation, capture in storage materials, and controlled release into a test chamber. The positron densities were still far below what would be needed for a practical propulsion system, but the fundamental concept had been proven. Matter and antimatter could coexist in an engineered system without immediately destroying each other. The December 2016 presentation that Drew Frisbee and other aerospace veterans laid out the complete vision. A spacecraft engine would use several kilograms of krypton-79 or similar positron-emitting isotopes as the antimatter source. Over weeks or months, positrons would accumulate in storage materials integrated throughout the engine structure. When thrust was needed, the positrons would be released into a reaction chamber containing deuterium fuel. The positron annihilations would trigger fusion reactions, heating the deuterium to millions of degrees. The resulting plasma would be magnetically directed out a nozzle, producing thrust. The performance numbers were extraordinary. Conventional chemical rockets achieve specific impulse a measure of efficiency around 450 seconds. Nuclear thermal rockets might reach 900 seconds. Positron dynamics' antimatter catalyzed fusion concept projected specific impulse exceeding 100,000 seconds. At that performance level, a spacecraft could reach Mars in weeks rather than months, reach the outer planets in months rather than years, and reach Alpha Centauri in decades rather than millennia. Weed acknowledged the engineering challenges candidly. The engine would need to handle plasma at temperatures exceeding those in the Sun's core. The magnetic confinement system would require superconducting magnets far more powerful than anything currently flying in space. The radiation shielding alone would be a massive engineering undertaking. But unlike warp drives or other speculative concepts, every component required known physics. It was an engineering problem, not a fundamental science problem. Dr. Frisbee, who had remained skeptical through the presentation, stood during the question period. His question was direct. You're claiming you can store antimatter at room temperature in solid materials. That contradicts 50 years of antimatter research. What makes you think you're right and everyone else is wrong? Weed's response was measured but confident. We're not contradicting anything. CERN stores antihydrogen atoms in vacuum using magnetic traps because they're studying fundamental physics. They need pristine antimatter for precise measurements. We're solving a different problem. For propulsion, we don't need perfect storage. We need adequate storage. We don't need to trap antihydrogen atoms, just positrons. It's a fundamentally different approach optimized for a different application. The technical questions continued for an hour. Could the system breed more Krypton-79 from natural krypton using neutron irradiation, creating a sustainable fuel cycle? Yes, the nuclear reactions were well understood. What about thermal management? Wouldn't the radioisotopes generate significant heat? Yes, but that heat could drive thermoelectric generators, providing electrical power for the spacecraft systems. How much antimatter would actually be needed? For a mission to Alpha Centauri, approximately 20 grams of positrons catalyzing several hundred kilograms of fusion fuel. 20 grams of antimatter. At CERN's production rates and costs, that would be economically impossible trillions of dollars for a single mission. But Weed's radioisotope approach changed the economics. Krypton-79 could be produced in nuclear reactors through irradiation of natural krypton. The isotope production would be expensive millions of dollars, but not impossibly so. More importantly, the antimatter production would happen continuously over months, not requiring massive particle accelerators running 24/7. The Defense Advanced Research Projects Agency, DARPA, representatives in the audience saw immediate applications beyond interstellar travel. An engine capable of reaching Mars in weeks would revolutionize military space capabilities. Satellites could be replenished or repositioned on timescales measured in days rather than years. The strategic implications were profound. By spring 2017, Positron Dynamics had secured additional funding from DARPA and private investors. The company raised $1.5 million through Propel X, a crowdfunding platform for deep technology startups. The investment attracted attention from aerospace giants. Lockheed Martin and Northrop Grumman sent engineers to evaluate the technology. The United States Air Force Research Laboratory opened discussions about potential flight demonstrations. But scaling from laboratory curiosity to flight-ready propulsion system revealed new obstacles at every turn. The positron storage materials that worked beautifully in benchtop experiments degraded rapidly when exposed to the radiation environment of space. The electromagnetic systems required to extract and direct positrons drew more power than early solar panel designs could provide. The fusion reaction chamber, which needed to contain plasma at 100 million degrees, proved extraordinarily difficult to engineer at small scale. Weed made a crucial strategic decision in mid-2017. Rather than attempting to build a complete antimatter engine immediately, Positron Dynamics would demonstrate the technology incrementally. First, prove positron storage in a space environment using a CubeSat, a small standardized satellite. then demonstrate controlled positron release and detection. Finally, integrate fusion catalysis and thrust production. Each step would reduce technical risk and build confidence among investors and potential customers. The CubeSat mission, dubbed Positron 1, was designed to fly approximately 2 kilograms of positron-generating isotopes in an engineered storage matrix. Sensors would monitor positron accumulation over several months in orbit. If successful, it would be the first demonstration of antimatter storage outside laboratory conditions. Launch was targeted for 2019. Then the setbacks began. In late 2017, NASA's NIAC program declined to fund Phase 2 research, citing concerns about near-term feasibility. Without that funding, Positron Dynamics lacked resources to fabricate flight-qualified hardware for the CubeSat mission. The launch date slipped to 2020, then 2021. Weed took on additional contracts with the Air Force and Draper Laboratory to keep the company solvent. The technical challenges proved more intractable than anticipated. The radiation-induced degradation of storage materials remained an unsolved problem. Even in the best cases, the material's ability to trap positrons declined by 50% after exposure to radiation doses equivalent to a few months in space. Shielding helped, but added mass that eroded the system's overall efficiency. By 2018, Positron Dynamics had pivoted to a different application, using positron beams for materials testing and medical isotope production on Earth. The antimatter propulsion work continued as a long-term research program, but near-term revenue required more conventional products. Weed found himself spending more time on business development and less on research. The dream of Alpha Centauri seemed to recede with each budget meeting and investor presentation. Yet the fundamental physics hadn't changed. The laboratory demonstrations remained valid. Positrons could be generated, stored, and released. The antimatter-catalyzed fusion reactions worked in principle. What was lacking wasn't scientific understanding, but engineering maturity. The countless refinements and optimizations that transform laboratory curiosities into practical technologies. By 2020, the broader aerospace industry had begun taking antimatter propulsion more seriously. NASA commissioned new studies on propulsion requirements for exoplanet missions. The discovery of potentially habitable planets around Proxima Centauri and TRAPPIST-1 created renewed interest in interstellar mission concepts. Research papers appeared analyzing antimatter propulsion architectures, optimal trajectories, and mission design. Dr. Ryan Weed's contribution to this renaissance extended beyond positron dynamics' specific technology. By demonstrating that antimatter storage might be achievable through radioisotope techniques, he had reframed the entire problem. Other researchers began exploring alternative approaches, different radioisotopes, different storage matrix materials, different confinement schemes. The field, dormant for decades, began generating new ideas. Competing concepts emerged. Dr. Gerald Jackson at H-Bar Technologies pursued antimatter-driven magnetic sails that would use antimatter to heat hydrogen propellant. NASA's Marshall Space Flight Center investigated antiproton trapping using advanced penning traps. The European Space Agency funded research into positron-catalyzed fusion using laser-driven compression. Weed's work had opened a door, and others were walking through it. The engineering challenges that positron dynamics encountered were being attacked by research groups worldwide. Materials scientists at MIT developed radiation-resistant positron storage matrices using diamond nanomaterials. Fusion researchers at Princeton Plasma Physics Laboratory demonstrated improved techniques for initiating fusion with positron beams. Superconducting magnet manufacturers began designing high-temperature superconductors capable of generating the magnetic fields needed for plasma confinement. By 2023, the technological landscape had shifted. The individual components needed for antimatter propulsion were maturing. What remained was integration, assembling the pieces into a coherent system. Positron dynamics had demonstrated key elements, but lacked the resources to build a complete engine. The established aerospace contractors had resources but lacked positron dynamics specific expertise in radioisotope antimatter generation. The solution emerged through collaboration rather than competition. In 2024, Positron Dynamics signed an agreement with the Air Force Research Laboratory to jointly develop a demonstration engine. The laboratory would provide facilities, testing infrastructure, and systems engineering expertise. Positron Dynamics would contribute its antimatter generation and storage technology. The goal was to build a subscale engine capable of demonstrating antimatter catalyzed fusion thrust by 2028. The engine design that emerged from this collaboration represented a synthesis of decades of research. At its core was a cylindrical reaction chamber, 30 centimeters in diameter and 1 meter long, fabricated from advanced carbon composites. Surrounding the chamber were superconducting electromagnets generating magnetic fields strong enough to confine plasma at 100 million degrees. Integrated throughout the structure were storage matrices containing krypton-79 isotopes, slowly accumulating positrons over time. Operation would proceed in pulses. Every few seconds, a burst of positrons would be extracted from the storage matrices and injected into the reaction chamber, which contained a small quantity of deuterium fuel. The positron annihilations would release energy, heating the deuterium and triggering fusion reactions. The fusion products, helium nuclei and neutrons, would generate additional heat, creating a plasma at extreme temperature. This plasma would be magnetically directed out an exhaust nozzle, producing thrust. The performance projections were extraordinary. Each pulse would generate approximately 50 newtons of thrustabout, the same as a small chemical rocket thruster. But the fuel efficiency would be 200 times higher than chemical propulsion. A spacecraft with a ton of antimatter catalyzed fusion fuel could achieve velocity changes of over 300 kilometers per second, enough to reach Mars in 3 weeks, Jupiter in 3 months, or accelerate to 10% of light speed over several years of continuous operation. Alpha Centauri, 437 light-years distant, would be reachable in approximately 43 years at that speed. A spacecraft launched in 2050 might arrive at humanity's nearest stellar neighbor by 2093, within a human lifetime. The journey would require approximately 20 grams of antimatter in the form of positrons, generated from several kilograms of krypton-79 over the course of the mission. The radiation challenges remained formidable. The fusion reactions would generate intense neutron flux, requiring heavy shielding to protect the spacecraft systems and any potential crew. The annihilation gamma rays, though less numerous, carried even more energy and penetrated most shielding materials easily. But these were known engineering problems with known solutions. Shadow shields, hydrogen-rich materials, and geometric optimization could reduce radiation to manageable levels. As of 2025, the demonstration engine exists primarily in computer simulations and component-level prototypes. The superconducting magnets have been fabricated and tested. The positron storage materials have achieved the required performance metrics in laboratory conditions. The reaction chamber design has been validated through plasma physics simulations. What remains is assembly, integration, and testing. The test campaign, scheduled to begin in 2026, will proceed incrementally. First, demonstrate that the integrated system can generate and store positrons over extended periods. Then demonstrate controlled release and injection into the reaction chamber. Finally, introduce deuterium fuel and attempt to initiate catalyzed fusion reactions and measure thrust production. If successful, the technology demonstration would validate the concept that Ryan Weed first proposed over a decade earlier. It would prove that antimatter propulsion, long relegated to science fiction, is achievable using known physics and engineering. More importantly, it would establish a clear development path toward operational engines capable of transforming space exploration. The broader implications extend beyond propulsion technology. The ability to generate, store, and utilize antimatter would enable entirely new categories of space missions. Antimatter-powered electric generators could provide kilowatts of electrical power for spacecraft systems, eliminating reliance on solar panels or nuclear reactors. Antimatter beams could be used for asteroid deflection, providing a defense against potentially hazardous objects. The energy density of antimatter makes it the ultimate battery. A kilogram of antimatter contains more energy than all the gasoline consumed in the United States in a day. Critics argue that antimatter propulsion, while theoretically possible, will remain forever impractical due to cost and complexity. They point to the decades of development still required, the billions in investment needed, and the fundamental dangers of handling antimatter. These criticisms echo objections raised against every transformative technology, from aviation to nuclear power to computers. Proponents counter that the economics will improve dramatically with scale. The first antimatter engines will be expensive, hundreds of millions of dollars for experimental systems. But mass production, assuming successful demonstrations, would drive costs down orders of magnitude. The Krypton 79 production costs, while high, are comparable to other aerospace-grade materials. The storage materials, once perfected, could be manufactured using techniques similar to those used for advanced ceramics or nanomaterials. The broader space industry is watching closely. If positron dynamics and its partners succeed in demonstrating antimatter-catalyzed fusion thrust, investment will flood into the field. Competing designs will emerge. Manufacturing infrastructure will develop. Within decades, antimatter propulsion could transition from laboratory curiosity to operational technology, following a path similar to ion propulsion or plasma thrusters. The human journey to Alpha Centauri remains decades away at minimum, perhaps centuries. But for the first time in history, a plausible technical approach exists. The physics is understood. The engineering challenges, while formidable, are being systematically addressed. The materials and components are under development. What seemed impossible is becoming merely very difficult. Ryan Weed's contribution to this transformation will likely be recognized as pivotal. By refusing to accept conventional wisdom about antimatter storage, by pursuing an unconventional approach derived from nuclear engineering rather than particle physics, he opened a path that others had not seen. His work proved that antimatter propulsion was not inherently impossible. It was an unsolved engineering problem. The parallels to other technological revolutions are striking. The Wright brothers succeeded in powered flight not because they were better engineers than Samuel Langley or Otto Lilienthal, but because they questioned assumptions and approached the problem differently. Henry Kaiser revolutionized shipbuilding not through superior knowledge of maritime tradition, but by applying manufacturing principles from other industries. Weed's breakthrough came from bringing nuclear engineering perspectives to a problem traditionally approached from particle physics. The psychological barrier that antimatter propulsion represented has been broken. Engineers and scientists no longer dismiss the concept as science fiction. They debate engineering details, storage efficiency, thrust-to-weight ratios, radiation shielding requirements. These are signs of a maturing technology, not a fantasy. The next decade will determine whether antimatter propulsion transitions from demonstration to application. The test program scheduled to begin in 2026 will provide crucial data. If the demonstration succeeds, funding for full-scale development will likely follow. Mission planners will begin designing spacecraft that exploit the new capability. NASA's next decadal survey for planetary science might include antimatter-powered missions to the outer solar system or even interstellar precursor missions. The implications for human civilization are profound. For all of recorded history, humanity has been confined to a single planet. The space age gave us the ability to visit neighboring worlds, but interplanetary travel remains slow and difficult. Interstellar travel has been completely beyond reach. Antimatter propulsion, if realized, would compress the solar system to manageable scales and bring the stars within reach, at least for robotic missions. Alpha Centauri, 437 light-years distant, contains at least 2 planets, including Proxima b, a potentially habitable world orbiting the red dwarf Proxima Centauri. Current telescopes can detect the planet's existence, but cannot image its surface or determine whether it hosts life. An antimatter-powered probe arriving at Proxima b in the late 21st century could return data that would revolutionize our understanding of biology, the origins of life, and humanity's place in the cosmos. The path from Ryan Weed's 2013 inspiration to operational antimatter engines will span decades and require contributions from thousands of scientists and engineers. But the journey has begun. The fundamental questions have been answered. What remains is execution. The patient, methodical work of solving technical problems, refining designs, demonstrating performance, and building confidence. The story of antimatter propulsion is ultimately a story about questioning limits. For 50 years, antimatter storage was considered impossible for practical applications. CERN's Penning traps worked for physics experiments, but couldn't scale to propulsion requirements. Conventional wisdom said antimatter had to be suspended in vacuum using powerful magnets. Conventional wisdom was wrong. Weed's insight was recognizing that the constraints were different for propulsion applications. Physics experiments require pristine antimatter maintained in isolation for precise measurements. Propulsion requires adequate antimatter storage at useful densities. By changing the requirements, Weed changed what was possible. The radioisotope approach sacrificed the purity and isolation that physicists needed, but gained the scalability and practicality that engineers needed. This pattern reframing problems to escape apparent limitations characterizes breakthrough innovation across fields. Einstein recognized that simultaneity wasn't absolute, enabling special relativity. Shannon recognized that information could be quantified, enabling information theory. Weed recognized that antimatter storage didn't require magnetic suspension, enabling antimatter propulsion. As of October 2025, positron dynamics continues its development work, now in partnership with major aerospace contractors and government laboratories. The company employs approximately 40 people, mostly physicists and engineers working on component development and systems integration. Ryan Weed serves as Chief Technology Officer, focusing on technical development while others handle business operations. The demonstration engine scheduled for testing in 2026 represents the culmination of over a decade of effort. If successful, it will validate not just a specific technology, but an entire approach to advanced propulsion. It will prove that the energy density of antimatter can be harnessed for practical applications. It will demonstrate that the limitations that constrained previous generations of researchers were not fundamental, but could be overcome through creativity and persistence. The journey to Alpha Centauri will be long. Even with antimatter propulsion achieving 10% of light speed, the voyage will take over 40 years. Communication with the probe will require 4.37 years for signals to travel each direction. The mission, if launched in 2050, would return its first data in approximately 2097, nearly 3/4 of a century from now. But that timeline, while long by human standards, represents a dramatic compression of what was possible before. Without advanced propulsion, Alpha Centauri would remain unreachable within any plausible mission timeframe. With antimatter propulsion, it becomes difficult but achievable. The stars transition from impossible destinations to challenging ones. The workers who built Liberty ships in World War II demonstrated that ordinary people could achieve extraordinary results when properly organized and challenged. They proved that traditional limitations on industrial capacity reflected organizational constraints rather than physical impossibilities. Similarly, the engineers and scientists developing antimatter propulsion are proving that the limitations we accept often reflect conceptual constraints rather than fundamental physics. Ryan Weed, like Henry Kaiser before him, succeeded by refusing to accept conventional wisdom. Kaiser knew nothing about shipbuilding and thus wasn't constrained by maritime tradition. Weed approached antimatter storage from a nuclear engineering background and thus wasn't constrained by particle physics conventions. In both cases, ignorance of traditional approaches became an advantage, allowing fresh perspectives on seemingly intractable problems. The ultimate lesson is not about antimatter propulsion specifically, but about human potential more broadly. The challenges we face, whether building ships in days, storing antimatter, reaching Alpha Centauri, or solving any seemingly impossible problem, yield not to superior intelligence, but to questioning assumptions, reframing constraints, and persistent effort. The antimatter engine that could reach Alpha Centauri doesn't yet exist. It remains a collection of components, simulations, and prototypes. But the path to its realization is now visible. The physics is understood. The engineering approaches are being refined. The funding and support are materializing. What seemed impossible is becoming inevitable. In November 1942, the SS Robert E. Peary launched after just 4 days and 15 hours of construction, proving that ships could be built in days rather than months. The demonstration didn't just produce a single fast ship. It transformed an entire industry and proved what dedicated people could accomplish. In 2026 or 2027, if the demonstration engine succeeds, history may regard it similarly, not just as a technical achievement, but as proof that antimatter propulsion is achievable, that interstellar travel is possible, and that the stars, for all their distance, are within humanity's reach. Ryan Weed stood in that conference room in December 2016, presenting concepts that conventional wisdom said were impossible. Less than a decade later, those concepts are being built, tested, and refined. The engine that could reach Alpha Centauri is no longer science fiction. It is engineering in progress, and that transformation, from impossible to inevitable, is perhaps the most remarkable achievement of all. It proves that human ingenuity, when unshackled from tradition and empowered by necessity, can accomplish what experts claim cannot be done. The journey to Alpha Centauri begins not when a spacecraft launches, but when someone questions whether impossible truly means impossible, or simply means nobody has figured out how yet. That is the enduring legacy being written in laboratories and testing facilities today. The antimatter engines being developed will carry more than spacecraft to distant stars. They will carry proof that human potential, properly directed and sufficiently challenged, exceeds the limitations that conventional wisdom imposes. The stars have always been there, impossibly distant, utterly unreachable. In the coming decades, they may become what they truly are: far away, difficult to reach, but not impossible. Just another challenge waiting for someone to figure out how.